Welcome to today's webinar, Go with the Flow, Modeling Fluid Structure Interaction to Design Next Generation Technology, brought to you by Convergent Science. Thank you for joining us today for this new installment of our webinar series. My name is Matthias Sulis, and I am part of the business development team at Convergent Science. I will be your host for today's event. I'm really excited for all of you to learn more about Converge and its capabilities in FSI modeling. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flow in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Now, it is time to introduce our speaker, Dr. Jassim Sadiq. He is currently a principal engineer in the new application development group at Convergent Science in Madison. His works focus mainly on fluid structure interaction and other coupled simulation, grid generation and manipulation, and efficient parallel computation-related project. He received his PhD in mechanical engineering in 2016 from Johns Hopkins University, where he used novel non-equilibrium integral wall models for simulating developing turbulent boundary layers over complex rough surfaces, including macro biofiled surfaces and urban boundary layers. Without any further delay, I will now pass the ball to Jassim. Thank you all.
Thanks, Mattia, for the kind introduction. Hello, everyone. Thanks for attending the webinar on fluid structure interaction modeling with Converge. As Mattia mentioned, my name is Jassim Sadiq, and I'm a principal research engineer here at Convergent Science. So let's dive right in and go with the flow and see how FSI can be used to solve engineering problems and help design next generation technology. So for those who are not familiar with the term FSI, or fluid structure interaction, refers to cases where there is an interaction of some movable or deformable structure with an internal or surrounding fluid flow. The solid could be a rigid body, in which case it undergoes a rotational and translational motion due to the fluid forces acting on it, or it could be a deformable body, in which case the solid deforms depending on the pressure and the fluid stresses acting on the boundary. So most FSI cases in the industry involve complex geometry and motion, along with strong transient flow features, which have to be captured accurately. Traditionally, this has been a substantial roadblock for engineers wishing to study these phenomena using simulations. Generating an initial computational mesh and maintaining that mesh quality can be prohibitively challenging and time-consuming. This is where Converge's autonomous meshing capability provides an efficient methodology and removes a lot of these pain points and enables the engineers to focus more on the physics and the results. So with Converge, it is no more difficult to set up a moving case than it is a stationary case. Converge's autonomous meshing strategy automatically creates a Cartesian mesh and a body-fitted grid around the object, and the embedding can be used to add targeted refinement in areas where users think it is needed. And we can also use AMR to dynamically refine the mesh where the physics required. So using this approach, it's very easy to model thin gaps and clearances arising from complex boundary shapes and motion. So here is an example of a swing compressor where you can see you have this fairly complex motion and thin gaps involved. And you can see how this simulation, if you were using a traditional mesh generation method, would involve days or weeks trying to get a quality mesh out of it. With Converge, from case setup to simulation to video release was less than 24 hours for this setup. So this kind of shows you how efficient it is to do these kind of simulations with Converge. Other point is that a lot of these FSI simulations involve other coupled physics as well. So you may have conjugate heat transfer, multi-phase flow, etc. So Converge has models that can handle a lot of these other phenomenon as well. So here is an example of an FSI simulation coupled with a multi-phase flow simulation. So this is a ship hull based on a DTMB 5415 geometry, which was one of the earlier designs for a US destroyer. So nowadays it's used mostly for benchmarking various cases. So here this ship hull is put in a very strong wave, and it is moving forward in these waves, and you can see how the predicted forces from the waves is causing the ship to be tossed fairly violently in the waves, and also how CONVERGE's autonomous mesh is able to conform to this motion and also give an extra refinement where it is required while reducing the grid requirements in other areas. So CONVERGE has a host of FSI features that enables it to do simulations of a variety of applications. So it has rigid 6 degree of freedom FSI models, and for deforming elements we have 1D, 2D, and even the capability to do full 3D deformations. So what we want to do in this webinar is to look at some application areas which highlight how FSI can be used in efficient design in these areas. So what areas do FSI simulations usually provide an impact? That is a very extensive list and would be difficult to provide an exhaustive list in a single webinar, but today we will highlight 3 areas. So the first is pumps, compressors, and valves. So in these kind of applications, increasing efficiency and reducing losses is of singular concern, and simulations are vital to test new designs and to understand the detailed physics that will aid engineers in designing ever more effective and efficient designs. Next, we will shift our focus to the horizon and look at applications related to offshore marine and wind energy, offshore wind turbines. So these are areas that have become prominent to address challenges regarding decarbonization our future. So there is a lot of challenges and opportunities in these areas to design better technologies. After that, we shall turn to biomedical applications. This is a newer area which has become prominent, I would say, in the last decade or so, and there is still a lot of open questions and challenges, and we will see how FSI can play a role in addressing some of these challenges. So let us go to the first application area, pumps, compressors, and valves. So here we will see how the contact models and 1D beam elements can be used in simulating these technologies. So for pumps and compressors, usually there are different regions of flow which are there are different regions of the flow which are controlled through valves, which are usually seated. So there's a valve seat, so the valve is in contact with the seat, and then it rises up, and then there's a stopper that constrains the motion of the valve. So the valve could be rigid or deformable. So in this example, you have a rigid flapper valve. So as the flow comes in, the valve tries to rise up. It is constrained by the stopper and the shaft, and so it kind of rattles in place, and you have this complex interaction between the valve seat, and the valve stopper. And you can see how the contact model is able to capture that feature, and also how CONVERGE is able to handle the flow in these thin gaps. Another example of a rigid valve with contact model is a plate valve. So the plate valve is usually present in reciprocating compressors in the refrigeration and the oil and gas industries. So here is a simplified example of a plate valve in a reciprocating compressor. So you can here see the cylinder region and the discharge region. So the plate valve is that orange valve that is sitting in its housing, separating these two regions. So as the piston compresses, the pressure rises up, which will cause the valve to rise up and the flow to go to the discharge region. So here you see a 2D slice view, which is also present in the on the right. So this kind of shows you what we are seeing in the animation. So as the pressure rises, the valve is pushed up, and as the flow goes into the discharge region, the pressure reduces and the valve comes back and hits back on the valve seat. So again, contact modeling is very important in this aspect. An example is a tubing pump, which is used in the oil and gas industry to transport fluid up the well. So here you have two ball valves. You have a stationary ball valve in a stationary valve seat, and you have a traveling valve that goes up and down. So as it goes down, the traveling valve opens, putting the fluid in up, and then as it travels up, the stationary valve opens and the traveling valve closes. So as you can see, as this goes back and forth, it can pull fluid from the bottom upwards. And here we are simulating both using CONVERGE, the stationary valve and the traveling valve. So I just want to mention this briefly. Now we will go into more details later. So CONVERGE also has the ability to do full 3D deformations using a third-party FES software called Abaqus. So this is a runtime coupling through API and an online simulation. So what this can do is that every time step, CONVERGE calculates the fluid forces on the solid object and transfers that information to Abaqus. Then Abaqus will calculate the deformations and get that information back into CONVERGE every time step. So just to illustrate it, here is the same plate valve case that we simulated just using CONVERGE's rigid body and contact modeling feature. Here now we are using a deforming setup from Abaqus. So from CONVERGE's side, it looks very similar to what we saw with the rigid body case. You have the pressure building up, the valve opens and closes. And here you can see the corresponding view from Abaqus's perspective. So Abaqus gets the forces from CONVERGE every time step. It calculates the deformation, and that deformation is passed back into CONVERGE, and so on, and the simulation progresses. In this case, there isn't much to see from a deformation perspective. It's mostly rigid, but we will see cases later where the deformation is more substantial. So talking about deforming objects, CONVERGE does have models to handle similar deformations within itself. So for example, we have this beam model where you can model a boundary using 1D linear Euler-Bernoulli beam elements. So this has a lot of applications, for example, reed valves. So here you can see you have this valve geometry, which is a 3D geometry, which is converted into an equivalent 1D representation using a beam axis. And then we use finite element method to convert that 1D beam equations into an algebraic set of equations. And then that is coupled with the CFD solver in CONVERGE to get a coupled simulation. So here we see an example of a reciprocating pump. So it has two valves. It has a suction valve, which is a cantilever beam, and it has a discharge valve, which is a clamped type of beam. So as the piston expands, it opens the suction port, and you can see how the cantilever responds. And then as it goes back up, you can see how the clamp beam opens and the discharge port is open. So we have a lot of our clients have used this to model their valve geometries, and we have had good matches for both the valve displacements. So here's an example of a suction valve and a discharge valve lift measurement, and also the pressure trace inside the discharge and the suction regions. Brings us to an end on the pumps, compressors, and valves area. Now let's shift the focus a little bit and look at offshore marine and offshore wind energy applications. So here we will see some other models that are becoming more important. So we will look at implicit FSI and 1D cable elements and some application areas where they are important. So what is implicit FSI? So the usual way we do a coupled FSI simulation is what is called a loosely coupled or an explicit approach. So what happens is that every time step you solve the fluid equations, you get the forces, and then you use the forces to move the FSI object, and the time step ends and the next time step begins. So this works well for cases where the solid density is much higher than the fluid density. So for example, if they become small. So here is a case with a density ratio of 0.2. So the solid is much lighter than the fluid. So here, this kind of loosely coupled approach fails very quickly. It becomes unstable. So you can see from the red line here, the acceleration blows up pretty quickly. So you need what is called a more tightly coupled or an implicit coupled approach. So in CONVERGE, every time step, if the implicit coupling is turned on, we pass information back and forth between the fluid domain and the solid domain till the forces converge. And with that approach, we are able to simulate this case in a stable manner. That's the green line. So here is a validation example, which is a triangular wedge, which is dropped into water. So as the wedge impacts the surface of water, you get a huge impact force. So without implicit FSI, the simulation would blow up at that point. So this is the, you can see we are able to capture well both the position and the velocity and match well with the predicted data from experiments and the simulation. So here is more of a real world example. So this was the same DTMB 5415 ship hull we saw in the introduction slide. So here we are looking at some more detailed predictions. So you have a uniform inflow coming here with a crude number of 0.8. And we are looking at the waves behind the ship hull, which is predicted in this case. So you can see the isosurfaces here. And what we do is we take lines at different distances from the ship and match it with the reference data. So you can see both our fixed trim and the FSI cases have a good match with the reference data at these different locations. We are also able to get a good match for the predicted forces for the pressure and the viscous force, and also predict the singage correctly for the FSI cases. Next is a propeller case, which is a surface piercing propeller. So this is based on the Potsdam VP1304 propeller, which we have validated for the fully submerged case. So here, what we said was that, okay, so this propeller is running at a fixed RPM that will create a thrust on it. And this thrust will cause the propeller to accelerate and reach a steady velocity where the thrust is balanced by the losses. And here you can see how we are able to capture very well the detailed flow structures on these propellers. So that is due to the CONVERGE's autonomous meshing strategy. So you can see here we are able to put in grid where it is required, and where you have these gradients, you can put in more grid and do an efficient simulation while still capturing the required phenomenon. So as I said, this case was based on a submerged propeller case that was validated for both thrust coefficients and Doppler velocimetry measurements. We can also do planing hull simulations with the propeller. So we have different models for modeling the propeller. So in the last slide, we saw how we can explicitly resolve the geometry and calculate the forces acting on the propeller. We also provide a series of rotor models which provide a reduced requirement for simulation without actually resolving the geometry. So I will not go into details in this webinar. So we have a wind energy webinar earlier, which has more details on these kind of models if you guys are interested in checking it out. So here you can see this propeller, which is modeled using a actuator disk model, is attached to a hull. And this whole system is an FSI object placed in water. And you can see as the propeller turns, it creates a thrust and also a moment, which causes the hull to shift up slightly and propel forward. In many offshore applications, mooring model is very important. So we said we want to go with the flow, but many times you don't want to go too much. For example, you don't want your offshore structure to drift away into the open ocean. So they are kept in place using a system of mooring lines. And to simulate offshore applications, you do need to have that physics present as well. So in CONVERGE, we have implemented a mooring line model based on a lumped mass structural model. So what we do is that we have a mooring line which connects an FSI object to a mooring point, and this we discretized into a number of segments. And at each segment, we write the force balance, the tension, the weight buoyancy, drag, etc. And that is partitioned onto the nodes. The mass is also partitioned onto the nodes. And with that, we get a system of algebraic equations. We also have a model that can model the impact of the mooring lines onto the seabed. So currently we use a penalty-based method or a soft contact. So using this, we have a system of algebraic equations for each cable, which we solve using RK4 with subcycling for stability. And to get the initial configuration, we use a static solver. So with this, we are able to solve a variety of offshore applications. I'll just show a couple of them in the next slides. So the first is a floating offshore wind turbine. So offshore wind energy has become very important in recent years. A lot of governments and institutions are spending a lot of time and effort in making them more efficient. So the EU, for example, estimates around 300 to 400 gigawatts of offshore renewable energy by 2050, including different technologies, floating offshore turbines, tidal wave, and floating solar. The US DOE has also started a recent energy earthshot called the Floating Offshore Wind Shot to tackle technical challenges in this area. So the idea is to bring down the cost of generation by at least 70% to $45 per megawatt hours by 2035, which is a very ambitious goal. And to do that, we do need to understand the phenomenon of floating offshore wind turbines and how these turbines interact with the surrounding environment and themselves. So that's why FSI will be playing a very big role in this area. So traditionally, in this area, people have used mostly engineering models, but we are finding out that they may not be sufficient to model these complex phenomena. So you have dynamic coupling between the wind and wave loads, cable dynamics, the rigid platform, the blade response, etc. So this is an example simulation using CONVERGE's FSI capabilities and multi-phase flow and wave generation capabilities. So these are kind of all the models that are used. Again, I won't go into too much details on each one of them. And here we are showing an example of a floating turbine based on NREL's OC4 platform and the 15 megawatt turbine. And we are measuring here the surge and pitch at various wind speeds. So you can see the wind comes in, the thrust of the turbine and the drag causes the turbine to surge back, and they are held in place by the moving cables, which also interacts with the seafloor, as you can see here. So we are able to get a good match for the surge and the pitch for a variety of operating conditions. And we have gone even further. So in the future, what we will have is that we need to be able to simulate offshore wind farms. So in those cases, the interaction between the wakes of turbines become important. So this was an example study we did to see how turbine responses are affected by other turbines and the environmental features. So you have the wave coming in, you have turbulence from the wind, and then you have the wake interactions between the turbines upstream and downstream. So this is a very interesting and complex phenomenon, and this is really exciting for us that we are able to do these kind of simulations very easily with CONVERGE, and we are excited to see where these kind of simulations will take us in the future. That is with the offshore wind turbine. Another example of the cable model in action is what is called a capping stack. So what is a capping stack? So a capping stack is used as part of a containment strategy when blowout occurs in an oil well. So you have a deep sea well that is used to extract oil and gas from the Earth's core, and if that blows out, suddenly you have a mixture of oil and gas releasing into the sea, which is not good news. So there are a variety of strategies to contain it. So capping stack is one of them. So this is an illustration of the capping stack in action, simulated using CONVERGE's simulating using CONVERGE. So the capping stack is connected through a cable to a crane. So the crane is modeled as a prescribed motion object, and that motion is transferred to the capping stack, which is a 6 degree of freedom FSI object, through the cable model. And the well blowout is modeled as a multi-phase flow. So it has an oil in the liquid phase and a gas in the gaseous phase coming into water, which is in the liquid phase. So it has a multi-phase flow, which in itself is a complex phenomenon. On top of that, we are adding both a rigid FSI and a coupled cable motion. So here you can see an animation of how this works. So here you can see, so you have a mixture of oil and gas boiling into the water, and the crane moves, and that motion is transferred through the cable onto the capping stack, and the capping stack is able to successfully cap the well. So with that, we put a cap on the offshore applications, and we are looking at the last of the 3 applications we talked about, biomedical. So this, as I said, is a more recent area for us, and I wanted to talk about a couple of models that we are looking at and how they can be used to simulate areas of interest in these biomedical applications. So the first one is a membrane model. And a good example of this is blood flow through arteries. So the arteries have compliant walls, so they act as membranes, and this compliance reduces the resistance to flow pulses. So these membrane models have other applications as well, like bladder tanks, parachute simulations, airbags, etc. So the model we have has a thin membrane assumption, and we are using linear constant strain triangles. And using this assumption, we can use CONVERGE's triangulation in Studio also to serve as a FEM mesh. Then we can write our equations in for each triangle, then assemble them together and get a system of algebraic equations which can solve the membrane motion, and that is coupled through the forces to the CFD solver. And here is an example of this one. This is a traveling wave in a compliant pipe. So you have a pipe which is initially quiescent, then you put in a delta P at the inlet, and then you see how it evolves downstream. So you can see as the pressure wave passes, it causes radial deformations on the membrane, and it reaches the outlet. So just to note here, the fluid and the solids have similar densities. So if you remember from earlier, when this happens, you need an implicit coupling to be active. So this membrane is also solved using an implicit coupling between the fluid and the solid domains. Otherwise, the solution will not be stable at all. This is done using CONVERGE's membrane model. We could set up the same case using a CONVERGE Abaqus co-simulation, which I mentioned earlier. So in that case, what we would do is that we would solve the fluid domain within CONVERGE, and then we would have an Abaqus simulation which would exchange information back and forth between CONVERGE. So we would transfer the forces to Abaqus. Abaqus calculates the deformation and gives back the information to us. So this also has to be done in a tightly coupled implicit manner, which we have added recently to CONVERGE as well. So the ability for Abaqus to be coupled implicitly. So we can have multiple iterations within one time step till convergence. And if we set up this case as a CONVERGE Abaqus co-simulation, we get a similar result as we do with just the CONVERGE membrane simulation, which kind of serves as a validation also of our membrane model. And here you can see how the forces from CONVERGE show up in Abaqus as these vectors. And you can see the deformation predicted from Abaqus. So, with these kind of coupled simulations, we get the ability to do more complex deformations. So this is an example, not from the biomedical field, but comes to us from the space domain. So this is a elastomeric diaphragm tank. So what is a diaphragm tank? So it is a positive expulsion device that separates the propellant compartment from the pressure end compartment. So these are used in launch vehicles to control sloshing during acceleration and also to push out the propellant in microgravity environments. So usually the propellant is hydrazine, but in experiments it's replaced by water because it's safer. So we are also using water in our simulations, and we are using helium as the pressure end. The diaphragm is a hyperelastic yaw model, and we are modeling the diaphragm in Abaqus, and we are doing an implicit coupling between CONVERGE and Abaqus. What we have a pressure end inlet, and that causes forces on this diaphragm, which is transferred to Abaqus, and it predicts these kind of complex deformation, which we are able to handle very easily in CONVERGE. And we are able to put in grid where the membrane boundary is, so we can resolve that better. So lastly, surface mapping. This is technically not a FSI simulation because there is no coupling between the solid deformation back into the fluid. So in many cases, we do not really want to calculate the deformation from the fluid field. What we have is some kind of information of how the surface changes with time. It could come from imaging data, for example. So the question is, so if we have some key frames of these surfaces, can we then model the deformation of that surface smoothly as a function of time and calculate the fluid motion caused by that deformation? The answer is yes. So we added a new surface mapping feature which does this, accepts surface files at specific snapshots of time. they are interpolated to create a smoothly varying surface deformation. So this is an example of a blade avoiding simulation. So you have these surfaces generated from imaging at particular times, and then we want to do the full blade avoiding simulation. So this is the surfaces we have from the imaging. So these are the volumes that were predicted, and then we do a 3D interpolation to calculate the intermediate surfaces, and this is the predicted volume calculated within CONVERGE, and the surface, this intermediate volumes are then used to calculate the surface deformation of each vertex, and then used to do these simulations. Lastly, this is something really new. It's not yet present in CONVERGE. It's more of an experimental feature. So we are trying to do full 3D deformations using finite volume approaches within CONVERGE itself. So the solid would be a different stream inside CONVERGE, and we would solve the Navier equations in that area. So these are some initial results. So you can see how we are able to do a vortex-induced vibration of the beam wholly within CONVERGE. And here we are predicting the necking of a steel bar, which has a plasticity as well. So this is really exciting and something that will open a lot of application areas as well. So with that, we are almost at the end of the presentation. So as I mentioned, FSI is an area that has a lot of impact in application design, and we saw that through example applications in 3 main areas: pumps, compressors, and valves, offshore marine and wind energy, and biomedical applications. We saw how these host of features in CONVERGE is able to simulate effectively a lot of these applications. With that, I thank you, and I hand over to Mattia. I'll be happy to take any questions.